Hi, and welcome to my talk. A good morning, afternoon, or evening to you, depending on whichever part of the world you're listening to this from. This talk is partly based on results produced during my master's thesis, as well as some new results, both of which we're currently writing up, and hopefully we will have this on the archive soon. Let's start with the motivation for the main questions that we consider. We know that Bell inequalities can be used to certify the non-classicality of correlations produced within a fixed causal structure, such as the one shown here. Causal structures in general can involve certain unobserved systems, which may be either classical or non-classical, as well as certain observed systems, which correspond to classical inputs or outcomes of measurements on the unobserved systems. Bell inequalities are constraints on the observed correlations, such that when they're violated, this certifies that some of the unobserved systems in that causal structure must have been non-classical. But this requires the assumption that the causal structure was indeed the original one, because if this were not the case and we had these additional causal dependencies given by these red arrows, we could use classical systems to violate Bell inequalities derived for the original causal structure. And a physical way to implement these assumptions is to ensure space-like separation between the parties involved, and also to ensure that they have good sources of local randomness to generate their inputs. So the message here is that it is important to understand what can be achieved using classical systems and under what assumptions in order to exploit the true potential of non-classical systems, both for foundational purposes as well as for practical applications. So going beyond fixed causal order, causal inequalities have been considered for certifying the non-classicality of the causal order itself. These are known to be violated in theoretical frameworks, such as the process matrix framework, where no fixed background space-time is assumed. But a clear physical understanding of such violations is still lacking. So an interesting question is whether causal inequalities can be physically violated within a fixed space-time. And as we have seen in the Bell case, it is important to model the physical assumptions needed for ruling out trivial violations of such inequalities. And within a fixed space-time, one can also consider events that are delocalized over it. Modeling these assumptions for these scenarios is not completely obvious. For example, one of the assumptions needed for ruling out trivial violations of causal inequalities is the local order assumption that requires the input to each lab to precede the output of that lab. But it is not clear how one can order space-time events that are delocalized, because measuring the space-time location at which they occur could decohere the whole process we're considering. We find that looking at the causal boxes framework that models events delocalized over a fixed space-time and comparing it with the process matrix framework that goes beyond fixed spacetimes, we can get interesting insights into these questions, which can have both foundational as well as practical implications. Let's first look at the preliminaries, which include the causal boxes framework and some other concepts that we'll need for stating our results. So a causal box can be thought of as a box with some input wires and some output wires that performs a completely positive map on the contents of the input wire. The states on these wires have two parts. The first part is the classical or quantum message, and the second part gives the space-time location at which this message was sent into the box or comes out of the box. These boxes can be composed either sequentially or in parallel, or using feedback loops that connect an output at a certain space-time location to an input in its future. So these boxes are closed under arbitrary composition, and more specifically, the state space of a single message can be given by the basis here. V here represents regular quantum Hilbert space, for example, that of a qubit, and T corresponds to a partially ordered set. For example, this could be a discretization of Minkowski spacetime. And by including the spacetime labels inside the Hilbert space, the framework can model superpositions like the quantum switch, which we'll see later. More generally, the state space of the wires are modeled as Fock spaces of these Hilbert spaces in order to allow for superpositions of different number of messages to be sent along these wires. For example, we can consider superposition where we have a superposition of sending no message and of sending some message, where omega corresponds to the vacuum state or sending 0 messages. We can also have superpositions of a message being sent at different times. Then the causality condition for causal boxes requires that a message produced at a spacetime location T by a causal box can only depend on inputs to that box that lie in the causal past of T. Now moving on, another concept we need for our results is that of causal inequalities. In the bipartite case, this can be formulated in terms of the guess your neighbor's input game, where we have two parties, Alice and Bob, who have freely chosen inputs A and B, and they're required to output a guess of the other party's input. If we consider ordered distributions, where, for example, if we have the order A before B, then B's input cannot influence A's output, as given by this condition here. So for convex combinations of such ordered distributions, we have this causal inequality. This captures the fact that in a fixed order, the party who goes later can at best output a random guess of the earlier party's input. These can, however, be violated in the process matrix framework using indefinite causal orders. Note that the framework already implicitly has assumptions that rule out trivial violations of such inequalities that can be obtained using two-way communication, as shown here. Now moving on, let's look at the quantum switch, which is claimed to implement a superposition of causal orders that has also been physically implemented in a lab. The quantum switch is known to provide certain computational advantages over fixed orders as well, so it is quite an interesting system to study. It basically implements a controlled superposition of the order of two operations. So given a control system and a target system, it's going to apply UA before VB or VB before UA, depending on the control. So let's look at the quantum switch in the two frameworks. We've got QS, which is a causal box that composes with the two causal boxes UA and VB, such that the resultant causal box implements the desired transformation. This can be modeled by taking T to be a set of 6 time steps. And now when time T equals 1, we have an initial state of the control and target coming in to this box. Then at time T2, we have 2 branches of the superposition where QS stores the control system in an internal quantum memory. And depending on that, sends the target state either to UA or to VB, and the vacuum state to the other box. Then at the next time step, the boxes have acted and they have internal counters that count how many times they're being queried on a non-vacuum state, because the vacuum corresponds to sending nothing. Then at the next time step, the output of Alice is going to the input of Bob, and the output of Bob will go to the input of Alice. And at time T equals 4, the boxes are then queried again. And we can see that both the counters are now set to 1. Finally, QS is going to look back at its internal quantum memory and output the control from there, as well as either the output of Bob or the output of Alice, depending on the control. And finally, we have the desired final state, and each of the operations have been applied exactly once. In the process matrix picture, you can think of the quantum switch as a 4-party process matrix, where there's a party C in the past who prepares the states and party D in the future who receives the final states of the control and target. The process matrix itself models the environment of these labs, the outside environment, which could correspond to an indefinite spacetime. The process matrix in this case can be completely described by this vector shown here, which encodes the channels connecting these different parties conditioned on the value of the control. Okay. So finally, this brings us to our results. Firstly, we look at the assumptions for ruling out trivial causal inequality violations. You can think of each local lab in the process matrix framework as being modeled as a causal box with an input wire and an output wire. So the first assumption on these local boxes is that at most one message of a fixed dimension can travel along the input wire or the output wire. And this is modeled by restricting the Fock spaces corresponding to these wires to allow only 0 messages, which is represented by the vacuum state, or a single message of fixed dimension, as shown here. This space here is the Hilbert space of the space-time stamps, such that the overall space is simply the tensor product between the quantum part and the space-time part. Now, the second assumption is that the local operation performed within each local lab is time translation invariant, which means that the operation acting on a quantum state entering each lab does not depend on the space-time location at which the state entered the lab. Thirdly, we have the local order assumption, which requires for each party AI with a non-trivial input space that their local operation maps the vacuum state at a given time to the vacuum state at the next time step. So this implements the local order of having an input before an output in each lab in a coherent way, because this tells us that any non-vacuum state at the output of the lab must have been preceded by a non-vacuum state at the previous time step at the input. Note that the first and third assumptions are indeed required for ruling out trivial violations, because if either of them were violated, we could have two-way communication between the parties and hence have trivial violations, as we have seen before. The second assumption, however, is not strictly required for this purpose, but in situations such as the quantum switch, the local time at which a non-vacuum state enters a lab could depend on the order in which the parties are acting, such that if the local operation depends on this time, this would reveal the order in which the parties are acting and hence collapse any superposition of orders that the process might be implementing. So here is a little illustration of how these boxes act. If nothing goes in at a certain time, then nothing comes out at a later time. But if a quantum state psi goes in at a certain time, we can choose some classical inputs or settings to measure this state, shown by these colorful buttons here. And at a later time, we have a post-measurement state, as well as some reading given here, which is the measurement outcome. Yes, so now we have our first theorem, which is regarding the quantum switch in the two frameworks. We find that if all the local operations satisfy the assumptions that we have considered, then the causal box of the quantum switch can effectively be represented by an operator living in these restricted Fock spaces that we have defined, such that this will map to the process matrix of the quantum switch when all the vacuum states and the time information are ignored. So this here is an equivalent way of representing the causal box of the quantum switch, which corresponds to what is called its sequence representation. So here you can see that each of the local operations of Alice and Bob are split into two time-like copies, which act independently due to our assumptions. So now if the control is 0, the green path will track the non-vacuum target state, which goes through Alice's lab at time t2 and then Bob's lab at time t4. And if the control is 1, then we have the non-vacuum target state going through Bob's lab at time t2 and then through Alice's lab at time t4, such that for each value of the control, only one of these boxes acts on a non-vacuum state and the other acts on the vacuum state. Now, ignoring the timestamps corresponds to combining the two boxes for Alice and the two boxes for Bob into a single box, which is always going to receive exactly one state. And then we can also ignore the vacuum states, and we have something that looks like the process matrix of the quantum switch. And this is what we formalize in this theorem. So we've seen that the quantum switch implements a superposition of orders, but it is also known that the switch cannot produce correlations that violate causal inequalities. So a natural question is whether it is possible to use causal boxes to violate causal inequalities once these assumptions are imposed. We find that at least in the bipartite case, the answer is negative, and we can formalize it in this way. So we've seen that we can model the local operations as causal boxes, and we can think of this causal box phi w as effectively implementing a higher order map on these local operations. It acts on them by composing with them to give a final causal box shown here, which can be described completely by a probability distribution. And we show that under the assumptions given here, this distribution cannot violate any causal inequalities. In fact, we also conjecture the same for the multipartite case, and we're working on a proof of this. So from this, it seems that causal boxes can only model controlled superpositions of causal orders, such as the quantum switch and generalizations of that. And a comment is due here. There is a similar framework proposed by Ognian Oreshkov, which in fact can model process matrices that violate causal inequalities. And this is in contrast to our conjecture here. The reason for this is the following. It is because the causality condition for causal boxes is actually a stronger requirement than simply requiring the probabilities to be valid for all local operations. This condition, in fact, restricts the internal structure of the channels involved, and it forbids them from forming time-like loops, even if these loops would lead to valid probabilities. So I think this would be the intuition for why causal boxes cannot violate causal inequalities, while these time delocalized systems can. So with that, I would like to now discuss the gravitational quantum switch, which is an indefinite space-time realization of the quantum switch. We've seen that the causal box description, which actually is also similar to the physical realization of the switch, actually implement a superposition that involves more than two distinct events. So in the case we've seen, this involves 4 events, where either we have A at time t1 going before B at time t2, or B at time t1 going before A at time t2 for 2 distinct times. We can consider another realization of the quantum switch transformation, which actually corresponds to a thought experiment where a large gravitating mass is put in a superposition of 2 different spatial configurations. This leads to superposition of the associated space-time geometries and hence of the causal order. And in this case, due to the gravitational time dilation, it is possible to have T1 equal to T2. And we actually can implement in this thought experiment a cyclic causal structure between 2 events. So this is better understood from this illustration, where we have 2 local labs of Alice and Bob with their local reference frames. In the first configuration, the mass is closer to Alice. In the second, it's closer to Bob. Now, if the party further away from the mass signals to the party who's closer, we can see that it is possible that the system is sent and received at the same time corresponding to the local frames. Now, if we put these configurations, these mass configurations in a superposition, we have a superposition of the orders where the local time does not depend on the order that is implemented, which is in contrast to the fixed space-time realization. So this tells us that the 2 realizations actually implement the same transformation, but have a very different physical meaning. In the first case, the fixed space-time realization, this corresponds to the causal box description and seems to implement an indefinite temporal order. While the indefinite space-time realization, which corresponds more to the process matrix description, seems to implement an indefinite causal order in a real sense. We can actually distinguish between these 2 realizations by measuring the local time at which a non-vacuum state is received. And it is showed in the paper that I've cited here that this can actually be done in a coherent manner. This brings us to the conclusions. We have compared the quantum switch in the 2 frameworks, showing the map from the causal box to the process matrix description, but these are physically very different scenarios, even though they implement the same transformation. We identified the assumptions for ruling out trivial causal inequality violations, and we found that under these assumptions, it seems like causal boxes cannot violate causal inequalities. And there are several interesting questions that one can further investigate. For example, whether it's possible to generalize the causal box framework to model indefinite spacetimes, and further, whether it's possible to formulate these causal inequality assumptions in a more device-independent way, and whether there are systems that go beyond causal boxes that can be physically implemented and that violate these causal inequalities. Finally, we have shown in a different paper that causal boxes can be used for composable security of a general class of relativistic protocols. And we did not find any advantage in those tasks from superpositions of orders. So it leaves open the question of whether superposition of orders can give any real advantage for these kind of composably secure cryptographic tasks. So with that, I would like to thank you very much for your attention, and I'm looking forward to your questions.